My dear student, today let us discuss about you know uh, integration. Everyone knows how to find out integration. So in our class 11 12 standard, we have we have discussed about integration, and here we are going to define integration in Lebesgue sense. Lebesgue integration. So it is the generalization of the concept we did in our lower classes. So yeah, since it is the generalization, we have to we have to start from the elementary things. We have to start from the elementary things. We have to borrow the idea from our class 11 12 or graduation integration, and then the concepts are generalized. The concepts are generalized in measure theory, integration in measure theory. First we are going to do in Lebesgue sense, then we are going to do in a general abstract space. So let us first talk about simple function. First let us talk about simple measurable function. Simple function. So here we are assuming that the domain of the function is the set of real number, whole set of real number R. So what is a simple function? Very important. A non-negative finite a non-negative finite valued function phi x. That means finite value means phi x doesn't take infinity or minus infinity. Finite value, okay, taking only finite number of different values. So in this line the function takes only finite number of different values. Okay, so it's called a simple function. It's called a simple function if if a1 a2 an are the distinct values taken by phi, and ai is equal to x such that phi of x is equal to ai, then function is given like this. Phi x is equal to a1 if x is member of a1, phi is equal to a2 if x is a member of a2, and so on. Phi is equal to an if x belongs to an. Okay, so let us see. Simple function means the generally function means function can take infinitely many values. Function can take infinitely many values. Function, the function is f is a function. It is defined from R to R. So and then the function has graph like this. So function has infinitely many values, right? Function is finite value means this is this much height is, suppose it is, say this much height is, say for example in the unit, say this is 10. So and this much height is how much? Suppose this is 4. Let it be 4. So the function takes every value between 4 and 10, right? So how many such elements are there between 4 and 10? So there are infinitely many such real number between 4 and 10. So this function, suppose if this function graph has like this, this is the graph, graph of the function like this. This much height is 4 and this much height is 10. The maximum value function can take is 10 and the minimum is 4. Okay, so between 4 and 10 there are infinitely many there are infinitely many values of the function. Okay, but this function has only finite. Finite means it is not infinity. The function is not going to infinity. So maximum value is 10, minimum value is 4. Function doesn't take minus infinity or plus infinity. So such function we call it finite function. Okay, but if it takes only finite values, suppose the function is like this. Suppose this is your a1, suppose this is your a1. So in a1 the function take, if x belongs to a1, the function take the value of a1 only. This is the height, same height, a1. Okay, so how much is this one? Small a1. All right, in this set a1 the function takes value a1. Okay, that means what? Phi value, suppose the function is phi, the phi takes value a1 only. Okay, and suppose from here, excluding this extreme point, from here to here, suppose this is a2, the function at the points of a2 it takes 0 value. Okay, say function, this function takes 0. Okay, so if x belongs to a1, all right, so function x is equal to 0 if x belongs to a2. And then suppose this point let us include in the next set a, this is a3. From here to here, including this endpoint, that is called is a3, set a3. At this point the function take, say, value a3. That means this height is a3. Okay, this height is a3, this rectangle, this height is a3, this is a3. Okay, so that means phi of phi of x is equal to a3 if x belongs to, say, a3. So how many values does the function take? There are only 3 distinct values the function takes. Number 1 a1, and number 2 a2 is equal to 0. Okay, a2 is equal to 0, and number 3 a3. Okay, so it has only 3 distinct values. The function has only 3 distinct values. In the set a1 the function takes the value a1. Okay, in the set a2 the function takes the value a2, that is equal to 0. In the set in the set a3 the function takes the value a3. So how many values does the function take? There are only 3 values the function takes: a1, a2, that is equal to 0, and a3. So such function we call it a simple function. Okay, it takes only finite many values, a1, a2, a3. Okay, so it takes only finitely many distinct values, a1, a2, a3, in this example. Right, in this example the function takes only finitely many values. Okay, so such type of function we call it simple function. Such type of function we call it simple function. Okay, and then let us see, in terms of characteristic function, let us define. In terms of characteristic function, let us define simple. How does it look like simple function? Okay, in terms of characteristic function. So then you can write this phi x is equal to a1 chi a1 plus a2 chi a2 plus small a3. This would be small a3, small a3 chi a3, you can write like this. Okay, so when x is a member of a1, when x is a member of a1, so x is not a member of a2 also, then x is also not a member of a3, right? So then chi a2x will be 0, so this part is 0. Chi a3x is also 0 because x is not a member of a3, this is 0. So chi a1x will be 1 because of characteristic function definition. Chi a1x is equal to 1 since x is a member of a1. So when you take member of x1, so this is 1, rest are 0. So what is the value of the function? The value of the function is a1, so it is okay. The definition is okay if x belongs to a1, phi x is equal to a1. Okay, so again, when x is a member of a2, what does it? When x is equal to a2, then x is not a member of a1, then chi a1 x will be 0, so this part will be 0. Alright, then chi a2 x will be 1, and this part is, it's okay, 1 into a2 is a2. And how about this one? X is not a member of a3, therefore chi a3x will be 0, so this part is also 0. The only thing remains this term. So then this is equal to how much? Then in that situation, phi x is equal to a2, but in our case a2 is equal to 0. It's okay. So agree the definition of the function, agree with the definition, new definition summation like this. Okay, again, suppose x is a member, suppose x is a member of a3, then how does it look like? Phi x is equal to, so if x is a member of a3, then x is not in a2 also, x is also not in a1 also. Then since x is not in the a1, chi a1x is 0, so this term is also 0. Since x is not a member of a2, chi a2x will be also 0, so this term is also 0. So x is a member of a3, therefore chi a3x is 1, so this is 1 into a3, this is a3. Okay, so alright, so that means what? In general, if the function, if the simple function takes, if the simple function takes a1 distinct, only n distinct value, a1, a2, a3, then an, and the value at a1, at the set a1, the function take a1, at the set a2, the function take value a2, at the set a3, the function value take a3, like this. Then the simple function can be written like this. Simple function phi x can be written as summation I is running from I, this is I, not n, I is running from 1 to n, ai chi ai x. The function can be, the simple function can be written in terms of characteristic function. In fact, this is a linear combination of characteristic function. Okay, so these ai's are what? Then you can define ai in, ai is equal to what? Ai is those point x such that phi of x is equal to small ai. So this ai you can define like this. This ai you can define like this. Okay, ai is the those point x such that phi x is equal to ai. Okay, so that means that means the simple function can be written as a the simple function can be written as a sum of linear combination. It is a linear combination of characteristic function. Okay, finite values. Since the function can take only finite values, so it is a finite sum of characteristic function. Okay, so again let us see about characteristic function, some property of characteristic function. So how we did, how for a simple function can be written as, this is summation I running from 1 to and ai characteristic function ai x. So it can be written like this. Okay, simple function like this. Okay, that means 1 in 1 where ai is equal to what is capital ai is equal to this is x such that phi of x is equal to ai. This is your ai, capital ai. All right, so what we know, let us see one characteristic function. This is a characteristic function. We have done one example that this is a function, this is called characteristic function. This function is measurable if and only if this set a is measurable. Means if the set a is a measurable set, this characteristic function chi a is measurable. Conversely, if this characteristic function chi a is measurable, then definitely the set a should be measurable. Okay, that means what, when the simple function is going to be measurable, so this is a what, this is finite sum of characteristic function, okay, multiplied by constant. All right, so this characteristic function chi a1 chi ai is going to be measurable if and only if ai's are measurable. Okay, so if ai is measurable, this characteristic function is going to be measurable. And then if this is just a constant number, so you multiply that function by a constant number, the resulting function ai chi ai is going to be measurable. So the only thing is that this phi x, and sum of measurable function is also measurable, that we have done. Okay, so this function, it is a sum of finite sum of measurable function when its ai's are measurable. Okay, so again conversely, if this function is measurable, then what, then the set ai, capital ai's, they are going to be measurable. So what I want to tell you is that this simple function is going to be measurable if and only if these ai's are measurable set. All right, if these ai's are measurable set, then this simple function is going to be measurable. Conversely, if this simple function is measurable, then what, this set ai, capital ai's, are going to be measurable. So this is the this is the idea of simple function. Okay, so then let us go back to our note. So simple function is like that: a non-negative finite valued function phi x taking only finite number of different values is called a simple function. Okay, it's called a simple function. The finite values the function takes are a1 a2 up to an, are distinct values taken by phi. Then you write capital ai is equal to x such that phi x is equal to ai. Then the phi x is equal to a1 if x belongs to a1, phi x is equal to a2 if x belongs to a2. So definitely then this phi x can be written as a linear combination of the characteristic function like this, that I have already explained. This simple function is can be written in this form only. So this is a linear combination because a1 a2 up to an, they are constants. Okay, so ultimately what, this simple function can be written as this finite sum of or linear combination of characteristic functions. Okay, so this is the thing we have. This is new idea, simple function. So this simple function is measurable if and only if if this simple function is measurable if and only if this set ai's are measurable. If this set ai's are measurable, then phi x is going to be measurable. If phi x is measurable, then these ai's are going to be measurable. Okay, so yeah, this is what I have written here. You can make it a or proper not, you can write it down. If this capital a1 up to an are measurable, then the simple function is measurable. If phi x is measurable, then necessarily the set a1 up to an are going to be measurable. They are going to be measurable. All right, so this is the idea of the simple function. Okay, this is the idea of the simple function. Now let us see, since the values are distinct. Okay, since the values are distinct, all right, so this a1 a2 an, they are distinct number. They are distinct. A1 is not equal to a2, a2 is not equal to a3, the an minus 1 is not equal to an. Okay, they are distinct. So let us So then this is definitely going to be, so a1 ai intersection aj is equal to phi if I is not equal to j. Let us see, if possible, if possible, let x is a member of ai intersection aj. Then what happened? Then x is a member of ai, x is also a member of aj. So since x is a member of ai, phi of x is how much? Phi of x is equal to ai. And since x is also a member of aj, phi of x is equal to aj. Okay, but what does it say? It says that ai is equal to aj, but they are different, no? ai is different from aj if I is not equal to j. So they are equal means I is equal to j. All right, so that means what? This is wrong. Okay, I is not equal to j. It is said here I is not equal to j, but here we come I is equal to j. So this is coming from our assumption, wrong assumption, that suppose this intersection is non-empty means it contains some point. So what is the possibility? The only possibility is that ai intersection aj is equal to phi. Why does it happen? It happened because the values, the function takes the finite values a1 up to an, they are distinct values. That means a1 is not equal to a2, a2 is not equal to a3, like that. Okay, so since a1 a2 up to an, they are different number, ai, capital ai intersection aj is equal to phi if I is not equal to j. Okay, this is the thing you have to remember. Suppose if r is the domain of the function phi, the whole of real number r is the domain of the function phi, then what? From here you can easily see that r is equal to r is equal to union of these finite sets ai. Okay, phi. Okay, r is equal to this finite set I. All right, ai. So this is this is easy. R is equal to union I running from 1 to small n ai. Okay, because the whole domain has been decomposing to finite sets only a1 up to an. Okay, so then their union should be the whole set R, or the domain of the function R. Okay, so now let us come to the very important definition, the Lebesgue integration. Okay, first we are going to define the Lebesgue integration to the simple function. From the simple function it will be extended to the non-negative measurable function. So first let us look at how the integration is defined on simple measurable function. Let phi be a simple measurable function. Phi will be simple measurable function if the underlying set a capital A1 up to capital An, they are measurable. This I have already explained. Okay, so then the integration phi dx. So let phi be a simple measurable function, then the integration phi dx is equal to this one. Let us see how does it come. So since ai's are measurable, measure ai are defined. Okay, then since this is a real number and this is a real number, their product defined, their sum is also defined, the integration is well defined, like that. Okay, let us see, let us go back to our knowledge of integration in lower classes, that is class 11 12, and then how does this definition comes. Let us see, that will make you more understanding. First let us go to this is window. Let us see how the integration is defined in our lower class. Let us see, suppose finite integration, definite integration. Okay, suppose the function is like this, the graph of the function is like this. This is the ordinate, this height, this is x-axis. Okay, this is y-axis, this is x-axis. All right, so this is like this. So this is the point A. At point A, value of the function is this much. This is f of a. So this is called f of a is called the ordinate at the point A. Okay, then you know, here this is b, and the value of the function at b is this much height. From here to here it is this much height. Okay, so this we call it ordinate at the point f of b. All right, so and then this is your f of x. This is the function, this is the graph of the function f of x. Okay, so height, the value of the function, like that. So then what we have is that, you know, that this is shaded region. This is the shaded area of this shaded region. This is the area of the shaded region. So from our elementary calculus, 11 12 level elementary calculus, so what is the area of this region? So area of this region, yeah, this is the area of this region. This is equal to, so what is the area? Area bounded by the curve x-axis and an ordinate at a and b. Ordinate at a and b. So ordinate at a and b bounded by this, you know, ordinate a at a, ordinate at b, this one, then the x-axis, and bounded by this curve. You have a region in xy plane. This is the shaded region. This is the shaded region. Okay, so this area of this is equal to how much? The area is equal to integration from a to b f of x into dx. So this is the area of the, you know, shaded region. So area of the shaded region is given by this definite integral, integration from a to b f of x dx. So this is the geometrical interpretation of the integration, finite integration or definite integral. Okay, this we have, this knowledge we have. Now suppose now let us come to the our simple function. So since the simple function takes only finite values, suppose at a1 this is the height, ordinate a1. Okay, at set a1, at set a1 this is the ordinate a1. At set a2, I mean excluding this point, you know, this extreme point, excluding this extreme point at this open set a2, suppose the function takes the value 0. Okay, there is no height, then 0 here. All right, so 0, some dark, so function takes the value. Then at a3, including this endpoint, at a3 suppose the function takes the value, you know, so a3, this is a3, and a2 here is equal to 0. a2 is equal to 0. Then what is the area? So what is the area of this figure? The function takes value what? So here according to the simple function definition, phi of x is equal to summation I is running from here. We have taken only 3 values, 3 ai phi chi of ai x. So here this one, the a2 is equal to 0, a1 is a1, and small a2 is 0, a3 is a3. So then according to this you know, definition of integration, according to this definition of integration, here the integration is very simple. You have to find out the area of the region. No? So area of the region, what is the area of the region? This rectangle, this is the rectangle, and this is rectangle. So this rectangle is you know, its height is equal to 0, therefore the area is 0 here. So area is equal to how much? Area is equal to, this is equal to a1, this is the height of the rectangle, okay, into breadth of the rectangle is the length of this set from here, that is, you know, from here to here it is length, no? That is measure of a1 plus, and 0, a2 is 0, a2 is 0, so a2 is 0, measure of a2, plus lastly, you know, a3, measure of a3, measure mean length. So length into breadth is a rectangle, area of the rectangle. Okay, so this area, this area, okay, and this is height is equal to 0. So ultimately this is equal to, you know, your area of this shaded region. So this is equal to how much now? So you can write this is equal to summation from, this is equal to I running from 1 to 3 ai measure, length means measure ai. Okay, so this is equal to how much then? According to the definition, our elementary calculus definition, integration means area. So this is equal to, this area is equal to integration, okay, phi dx. This is the function, general function f. But in our case the function is simple function. Okay, so integration of this simple function, okay, is given by this sum of the, you know, area like this. Okay, so then in case of general, you know, phi n values, if you take the simple function takes n values, then integration of phi dx will be what? In summation I running from 1 to n ai, you know, chi measure, this should be measure ai. All right, so this will be measure ai. So integration phi dx simple function is equal to, you know, ai measure ai. Okay, so this, from this elementary calculus definite integral definition, now we have defined the integration to a simple function like this. Okay, once if we are able to define, or once if we have defined definition of integration to simple measurable function, then we will extend this definition to, you know, any function, non-negative function, any non-negative function which is measurable. So it will be extended. Okay, so you have to, you know, you have to understand how, why we define integration, you know, why we define integration to simple measurable function by this, you know, because the analogy, you know, the analogy, you know, so the integration, definite integration of, you know, of a function is given by the area bounded by the x-axis, you know, ordinate, and then the graph, the region area. So taking idea from that one, so when you talk about a simple function, graph means area means like this. So area is what, you know, area of the, this is rectangle, so area of the rectangle is equal to height of the rectangle into breadth of the rectangle. Breadth of the rectangle is just the measure of the set a1. Okay, here breadth of the measure, breadth of the rectangle is what? Measure of the set a2, like that. So then this will be total sum of the area. Okay, so that is integration is like this. Okay, so that is how we define integration to a simple measurable function. That is how we define integration to simple measurable function. Okay, so then this is a very important. Okay, and then now let us define integration to non-negative measurable function. How we define integration to non-negative measurable function? After defining integration to simple measurable function, now we are going to define integration to non-negative measurable function. Okay, so for any non-negative measurable function f, for any non-negative measurable function f, no, for any non-negative measurable function f, the integral of the function f, it is denoted by integration f dx, is given by this, you know, supremum of, you know, you already knew that we can find out integration of simple measurable function. Okay, where the supremum is taken over all measurable simple functions phi, such that phi is less than or equal to, you know, f, phi is less than or equal to f. Okay, so this is the, you know, this is the definition of integration of a non-negative measurable function. So what to do? You think about all simple measurable functions such that phi is less than or equal to f. You think about all those simple measurable functions such that phi is less than or equal to f. Okay, then since you know how to find out the integration of simple measurable function, you find out the you find out the integral of all those simple measurable function. So you have lots of values of simple integration of simple measurable function. Then you take the supremum of all those values. The supremum is the integration of the non-negative function, non-negative measurable function. Okay, the supremum is the non-negative measurable function. Okay, so how we do here? Let us again come to this one. So you think about, you already know how to find out the integration of a simple measurable function. Then you have a non-negative function phi f. Okay, you think about all those simple function which is less than or equal to f. Okay, so phi is less than or equal to f means at every point of x you evaluate phi x. Okay, so this is less than or equal to f x. Okay, at every point of x. So you think about all those simple measurable function which is less than or equal to f. Okay, then you can, since you know how to find out the integration of simple measurable function, this is a non-quantity, this is some real number. Okay, so such simple measurable function, how many are there? So there are lots of such simple measurable function which is less than or equal to f. Then at each simple measurable function you evaluate the integration like this. So how many such values? There are lots of such real number values are there. You take the supremum of this one. Okay, the supremum of this one you take. That supremum is, that supremum is integration of f. Alright, that supremum is equal to integration of f, and this integration is called Lebesgue integral of this function, non-negative measurable function f. Lebesgue integral of this non-negative measurable function f is given by this formula. Supremum integration phi dx, where the supremum is taken over all simple measurable function such that it is less than or equal to f. Okay, it is less than or equal to f. So this is the idea of defining Lebesgue integration. Okay, Lebesgue integration. So first we have to define what is simple function, then what is simple measurable function, then how we define integration on a simple measurable function by borrowing the concept of our 11-12 standard geometrical interpretation of integration. From that you borrow the idea and define the integration on simple measurable function. Okay, once you know how to define the integration on simple measurable function, then we define the integration of non-negative measurable function using this formula. Okay, so this is how we define Lebesgue integration for a non-negative measurable function. Okay, so since this is a new idea, I don't want to go to the direct theorem. Okay, try to assimilate the new concept, new definition, try to digest. In the last class was a little bit lengthy, so this one, I don't want to give theorem here. Try to understand the definition very clearly, how the definition is defined, how we borrow the concept of integration from our calculus. Okay, idea, and then we define the integration to simple measurable function. Then we define to integration of a non-negative measurable function. Okay, so next time I will give you some theorem, some result, and for today I want to stop here. Okay, thank you very much. I hope all of you are watching it and you understand it. You can copy the note after pausing, and whenever you have some difficulty, whenever you have some confusion, don't hesitate to call me. Okay, so many people also call me, I explain them also, so why not you? If you don't understand, I am there for you. Okay, don't hesitate, just talk to me and I will explain to you.